Welcome back to this important deliberation again to discuss about the implementation norms with its operational and challenges and the solutions to these challenges. For this session, we would have Mr. Subhendu Podarji, who is already there with us. We will start the session with Mr. Podar. By the time I will connect with Ms. Banerjee and other speakers, including Mr. Anshuman from TERI and Dr. A.V. Singh from Bajaj Group. Podarji, you may start with your presentation, sir.
Thank you. Let me share the screen.
A.V. Singh sir is here. Sir, namaskar and welcome to the session, sir.
Namaskar. I'm trying to...
in the meanwhile, can I request Dr. A.V. Singh sir to start his presentation?
Reason is actually I want to request, reason being that I'm having some other meeting at 12:30 by chance.
Okay.
So it is important meeting, therefore I'm requesting. So I can share my document from here also.
Yeah, you can. Podar sir, I have stopped your presentation. I think Dr. Singh has some.
Okay,
sir. This time Dr. A.V. Singh from LPGCL, and because there is a lot of communication gap, but finally actually I'm having some other meeting also. So finally I am here with sharing the experience what we are doing, particularly optimization of water consumption in power plant. And one thing very important, that I am not here as a teacher, but I am just going to share how we have reached to the level where most of the power plant is still struggling. A reason is that is we have taken each and every aspect at the same time, because entire our water consumption is totally based on the saving. So first of all, I'm going to start from where I am taking the water. But I am taking water from the Rajghat Dam, and the dam is 50 kilometers away, and we are taking through the pipeline, closed pipeline, and it is with the we are having the agreement with the UP irrigation, and that too after saving the water, because all the Rajghat canal, which is not lined, we have made first lined, and after that what the water saved, that water we are taking for our power plant. So entire model is total sustainable model. So everything what we are taking, that is the water saved by the lining the canal. So before that, just it is my always been that what you are going to be measured, that is going to be controlled. If you are not having the measurement device, so nothing is going to be controlled. It is 100% sure. So just I have given the diagram, and we have taken each and every activities where water is going. So that is for the we are having two reservoir of the 40 lakh meter cube in our plant site. From there we are taking the DM plant and the process water. So this is the way the water we are utilizing, and it is going. And you see the water which is required only for the what is the evaporation and drift loss and the blow down, and this is the water which is required as a makeup water. Beyond this, everything we have controlled. You see the from the evaporation drift, it is from the cooling tower basin, then it is going to the side stream filter, and from there it is ETP. And the blow down water we are directly taking for the ash handling, and the excess water is going to the RO system, RO reject, and then it is recycled back. This is the water diagram in power station. That is the miscellaneous water which is coming from the different plant, different segment to the ETP. Here also the side stream filter, DM water waste, and the guard water pond, it is everything coming in a guardwater pond, and from there it is ETP. And then we are taking to the ash handling plant and bottom ash and recycle back. And one thing I want to emphasize more, that we are having the high concentration slurry disposal that is not being used, because most of our fly ash, almost 100%, is going to the cement plant. So that is the saving we are doing, because here water we are using for pushing the fly ash to the dike. This is the water balance, because it is very, very important. If you want to control the water balance is extremely essential. And you see that the water A and B, Q is equal to A and B is going to be C plus D plus E. Everywhere we have put the water meter, so that if any plant is going beyond the design or what the status they are maintaining, immediately it is reviewed and then corrective action we start taking. So this is the system we are having, and it is displayed everywhere. They are knowing what the water requirement of their plant and their process. Then see the overall picture, that is C is F plus G plus H and G plus G1 L I and J, and K is going to be J L D1. So it is very, very close system, except drift and evaporation loss, entire thing is trapped. So excess water is going to the RO system, and from there it is coming to the recycle back to the cooling tower basin. Now I am coming to the point, what is design? You have to see, most of the people, when you are going in the plant, if anything is going here and there beyond control, most of the people or the technical person always been saying that it is, they are defect in design defect, it is design defect. But it is our belief, when it is designed, it means it is going to happen and it is going to be achieved. So don't consider that designer is at wrong place. So that is the belief we are having, and therefore we are taking what the drift and evaporation loss per hour per megawatt, what is the blowdown, what is the service water and other DM town filtration and chlorination, and total it is going to 2.9 to 3. And here I would like to emphasize that the recent notification which has come from the CPCB, that is giving the water utilization is 3.5 meter cube per hour per megawatt. But our design is still quite conservative. It is from 2.9 to 3. Now I am coming to the actual what we are achieving. It is actual water being consumed at our plant, and instead of 5 COC, we have gone to the 7 COC. Therefore, a lot of saving because of high concentration. And this is the blowdown and service water, and the total water 2.02 meter cube per hour per megawatt. If you are having belief that it can be achievable, then you can achieve. Otherwise, if you are thinking that it is not, then you cannot. So we have to believe. Even we are going beyond below 2 meter cube per hour per megawatt, that is the aim we are having. And I would like to emphasize that Government of India has awarded us with the citation as well as the cash award also. So this is the reason, because the entire team, the director has come from the Ministry of Jal Shakti. They have visited our plant, remained 3 days. They have touched each and every activities, and finally they have awarded this is the best plant, particular in the India. So this is the optimization exercise with the GLD, zero liquid discharge. We are maintaining a reduction of ice water ratio, because we have seen that ice water ratio as per design is 1:11, and we have reduced it to 1.8. Slurry concentration of high concentration disposal system, that is 60-70%, density is 1.6. Saving in the CHP water, all the saved water shall be circulated in RO and skewed, reused at the city makeup. Service water, we are always been having the alert. If any events, most of the plant you have seen, the fire hydrant system always been open. Some of the other workers are, they are just washing, cleaning, and doing something, and it is being in the process, but it is totally restricted. Any drop in the pressure, immediately it is reflected, and we can see where the problem is. See, we optimize the cooling water flow as to evaporation and drift loss remain 1.8. And we have gone for COC 7, water consumption 2.9, less saving. That is and this is the reason we have achieved 2 instead of the permissible, which is given 3.5. What the strategy we are having, that is, I think it is reflected on the screen. Flow measurement to all location, optimize cooling water flow down, correlate with the condenser performance and the pump performance. Installation of flow meter in the riser of cooling tower to compare the flow. This is how we are going to optimize the water. And we are also checking the evaporation, as well as it is always been discussed at the top level, particular monthly. That is what the design and what we are achieving, or why, how we are achieving. That is because the most of the water is being consumed, particular in the ice system. Therefore, it is also monitored very regularly. And there is tremendous water saving potential in fire water, heating and ventilation system, and CHP. These saved water is directed to the ETP and reutilized. At lower loads, because of lower ice generation, there will be further saving of water. And I have seen the water consumption dropping from 2 to 1.8 to 1.9 meter cube per hour per megawatt when load is less. And therefore, have the water balance checked periodically, measure the flow operate GLD properly. You will achieve the water saving in the coal-based thermal power plant, which is the need of hour. If you are going to permit me, then I will share another presentation how we have. So if you are going to permit, we are going to, because we are operating our plant in the water scarce area, that is Bundelkhand region, and there, there is no water. Even you cannot operate a pump, hand pump.
Sir,
they are dependent fully on the river.
Sir,
so we have done a lot of. Yes, please.
Your presentation is not visible.
No, I am not presenting, sir.
Okay.
At present, it is presentation is over, sir.
Okay.
Should I repeat?
No problem. Please go ahead.
No. So what is happening? I am just going to share. This is the water conservation, particularly in the plant, and even the plant boundary also. And the rainwater what is coming, particularly in the monsoon season, we are also conserving. And the entire area by our work, the water level has come at least 10 feet up. And therefore all the hand pump is working and everything is very, and earlier it was a single crop, but now it is a 3 crop. They are taking all the farmers. They are very happy. Now you can raise the question how you have done it. So if the chairman is going to permit me, then 10 minutes I will take more, and I'm going to show how the water is conserved within the plant and outside the plant, and making the groundwater tables considerably high.
The floor is yours, sir. Probably you don't have to ask permissions.
Okay. So I'm going to share the presentation again, a different presentation, how we have done the water beyond the process water.
Yes.
Now it is visible.
Yes.
So see the on an average 3 to 3.5, and we are 1.8 to 2.52. Waste generation is 0.1 to 1.5. We are 0.08 to 0.12. Now you see the entire plant area, even in the radius of 15 kilometer, our plant is encircled with the 2 rivers, that is Sajno River and Utari River. And we, in order to retain the water of the river, we have made the check dam, ponds and borewell, nala revival, percolation of well and borewell. You can see the number that is inside plant. I am talking not outside. Outside I will take you differently. That is check dam is 1. Whatever the water which is coming because of rain, that is controlled. We are having pond and borewell 1, Nara revival 880 meter within the plant, so that the water remain always in the plant. We have also made the percolation well, and borewell is 24. So this is the total network we have made, and we are retaining the water and charging the groundwater. Water increase up to 5 feet, ensuring ability of the water round the year. Water flow increase from 8 to 10 months, and the 52 wells and bore wells are benefited in surrounding of the pond boundary. The moment the water is charged, the well and bore well, their water table has come up. Area benefited in and around plant is 1300 acre, and we have also planted 1,80,000 forest species, because this species is going to be survive in the plant, because it is a rocky area. Therefore we have taken the forest species, and 120 we are going for the bank covered with the grass seed. And one technique we have evolved, that is the seed balls. I think most of the people are knowing, instead of plantation we are putting the seed balls, where the seed are kept in between some of the making in a different way with the fertilizer, organic fertilizer, and when it is spread, it is going to be everywhere the plantation is. Storage capacity of different structure we have increased from 2881 TCM. See how we have 37, we have reached to the 37 villages, almost 30,000 families, and 1 lakh population we have covered. See how we have revived the Nala. And this is the water, particular in the month of April and May. How we have made the Nala revival. This is the structure sectional drawing, just to understand how it is made. See, this is the river. and the check dam. Now it is the peak summer season and the water is still retained in the check dam. This is the pond. We have gone for deepening up this. Our colony is seen just in the background. This is the officers colony. It is outside plant boundary and this water is retained. We have deepened the pond which is existing earlier. How we have made and what is the drawing, it is also reflected here. How we are making the bore well so that water can be charged to the ground. Therefore, we are putting all, it is within the plant. This is the drawing, sectional area. How you see, earlier it was like when we are making the bore well, and now the water is charged and our Mother Earth is going to be full of water. We have constructed 5 such bore wells. Percolation well. This is the check dam on the rivers. And one new thing we have evolved, that is boriband. We are putting in the bag, sand in the bag, and the local nala we are going to fill it in between and then water is retained. So it is a no cost check dam, and we have made such type of check dam at least 3 to 4 in and around the plant so that water retained. This is a rocky water scarce area. You can see the plantation in background. See the river and the Nala revival. See the pond, it is deepened. Therefore, all the water which is coming because of rain during the monsoon, that is, it is abandoned mines. We have deepened it and make the slope, directed the flow, and now it is full of water. And this is going to serve as a reservoir for irrigation for the village people. The total structure which is made in and around plant, 2 rivers, 6 check dam, 4 check dam renovated, 10 revival, 28 farm developed in the abandoned quarries, 20 quarries, that is we have mines we have taken, 93 boriband established in and around plant so that water can be retained and it can be utilized gainfully, particular for the irrigation from one single crop to 3 crops. See how the farmers going to be benefited. They are happily sowing their tomato. We are not limited. It is the Goshala shelter, and the entire village we have converted into one color so that it can be identified that this village belongs to the LPGCL. Any people who is coming from out, they are saying this is the adopted village of LPGCL. 4,800 family has directly benefited. You see the help group formed. We are working very at a ground level. This is our COO distributing the cycle to the girl child. This is the tomato and the different vegetables. See the size, how happily they are sowing. One of my employees is just sowing the bagan aapke samne. These are the biogas, 40 biogas we have given. and 500 toilet we have provided. This is the entire area. You can see the aerial view. This is the temple also developed by us. And one thing very peculiar we are doing, that is very important. You have to understand, any employee or the worker, if are having their birthday, one day is fixed in the month where each and every birthday boy is required to put a plant. This is the birthday plant. You are seeing in the background, and how we are celebrating. Nameplate is also put. Their birthday is, or they are planting a tree. This is the toilet. This is our services. Thank you very much. This is the outside, inside, as well the process water, how we are saving the water and what importance we are giving to the water. And the entire area which is water is scarce now is full of water. Anybody can come and see the impact, which is very, very quite good impact, and the people are quite benefited. Thank you very much for giving the opportunity to present something. And we are always been the learner, and we believe that until unless we are going to believe that it can be conserved, you can improve, you cannot improve. Therefore, we always believe that improvement can be done every time. Thank you, sir.
Thank you, Khatri sir. Thank you so much for joining us. I will request Mr. Podar to further present his slides from his deck.
So I may take permission to leave, sir?
Yes, sir. No problem.
Thank you. Thank you very much, sir.
Podar Sahab, you could proceed further.
Yeah, good afternoon.
You're audible.
Yes. Yeah. My friends, seniors, and all experts here, I'll start my presentation with an apology that I, being a straight talker, I may be talking little harsh things. So in the last session, the topic was that why 51% of has already been implemented and another 49% has not been implemented. And host was right about it, that there is no push from the regulator side, maybe. But my point was that this is due to there are technological solutions for everything, but only barrier is always attitudinal. So here, in my opinion, the barriers were not only attitudinal, there may be certain economical barriers also. But let me just quickly go through, because for the last few sessions, we have been hearing various solutions. Even during these panel discussion, we were discussing a lot of solutions. And I think Dr. Soumitra Banerjee is one of the experts in this line who is used to give solutions to many people. I am also in consulting, and I'm trying to give solutions to many people. And everywhere I go, I find the same thing, that if they are interested, then only I can give them. Otherwise, my efforts will be useless. So at the very beginning, I will request all of my thermal power station colleagues, please come out of the ego barrier that everything has been done and nothing can be done extra. What has been transpired from the earlier discussions, that every plant is different. Every plant has a specific solution. So all of us should not copy others. If somebody in a seminar is telling me that he has implemented 15 COC, and currently I am operating my plant at 5 COC, and from tomorrow I'm very excited that I will operate my cooling system at 15 COC. it may not be possible. So for that, we need to study the entire thing, and we need to do the corrections in a balanced way. So that is my experience tells. So if I correct something somewhere, it may have some impact on other system. So I have to take care of that also. So what I have told that that I have worked in plants which were consuming even 7 cubic meters per megawatt hour, and currently, or you can say that the last plant I had worked for was around 2.5. So quickly I'll go to the areas which have been always discussed, that these are the few areas where we can touch upon. And Dr. Ganguly has established that the only CW makeup system is the most important area where we can do a lot of things, because this area is around 80 to 85%. The total consumption of water, this makeup system, out of the entire consumption, it consists of 80 to 85%. So anything done in this area will be very effective. Then why optimization is necessary? We have all discussed that the available resources are day by day reducing, and the key input to thermal power stations, and we have no escape even today. And another new thing come up today, that the regulations have forced us, or rather forcing us to install SOx and NOx control systems, especially in the FGDs, will be using water. So that is tend to increase, is even though slight, but it's tending to increase the water consumption there. So I have already told this. So what we can do, because talking about air cooled condenser and these on that, the new technology is not applicable to existing thermal power plants. Existing thermal power plants which are ready to operate in the new regulated regime need to do something to be compliant. Yes, the new power plant which will be designed today or tomorrow may consider the new technology adoption, but the existing plants, adoption of new technology in many areas may not be possible. So they have to bear with the existing systems. And as has been explained by many speakers, that what we should have everywhere a clear measuring system, data collections, and proper utilization of those data, correlation, utilization of those data. But I have only listed out few things which are inside the plant, not outside. So it may be visible. So we should do regularly. So maintenance of cooling towers and improving operational COC requires expert advisors. Also, sometimes the O&M staffs may not be able to do the correct judgment. So in that case, of external, so in that case, sometimes it happens that the existing O&M head may think that external help is not required. They don't know much about our system. We know about our system. But sometimes it happens that if some external people come, he may have different viewpoints, different eyesights, and he can identify different areas which are overlooked by the regular operating people. So in my conclusion, the water consumption optimization is the need of the hour, and generating companies must accept the reality that we should start working. And every plant may have different action areas. So engineered solution is required. So don't copy, go for specific engineering. If your friend's plant has adopted something, please do not copy and adopt that. do your plants engineering. Thank you very much. If you are, you can contact me in my number, which is available with the Mission Energy also. Thanks. Hello.
Yes, Mr. Bhatta.
Yes, I have concluded my presentation.
So I would request Mr. Banerjee to further proceed.
All right. Thank you so much. Uh, you know, we have understood for last 1.5 days that what is required and why it is required. And since I did this through my hand in two of the big giant power plants, so I will share my experience that how I could achieve two and how 1.74 is also achievable. These all are the things which you have already heard from people, that what MOEF says and what Terry has done. We'll also hear it from Terry that what is their next part. And now MOEF has come back to 3 cubic meter. That also is known. So these are the things, the how part. Why and what we have already gone through. The how part is the first and most important part is create a water balance for your power station as accurate as possible and populate the data, whatever you get, and populate it every day. In fact, have the meter installed. Turbine type meters are there in some of the places, but people were vouching upon some wears and V notches and all those things. Rather than that, we should have good kind of meters. Nowadays, smart meters and the connectivity with IoT is available that can be used as we use in energy management system. Then cleanse and analyze the data. Data will come to you. Some days it will be very high, some days it will be very low. You have to delete the exceptions, and you will understand from this the point where the consumption is actually high and points where collection and recycling is possible, and monitor them continuously. Monitor the data and the outcome, the information it gives continuously. The macro controls which you can have is coming back to the ash clarifiers and then using it back, and this all perfectly as per the design. So we need to have a firm water balance. We need to have the meter installed, and nowadays smart meters are available which can fetch you data at a central point where you need. And this you are already using in the energy management systems at your plants, and you can use all these things for water management system as well. Then whatever data you get, you please cleanse them, remove the top highs and bottom lows, and then analyze the data, trend it, and you will arrive at the point where the consumption is high, points where collection and recycling is possible, and you need to monitor them continuously. The macro controls which you can have is the ash handling system and recovery ash water. This system should work perfectly. All the clarifiers, all the dikes, the seepage should be the lowest possible, and the water should be recovered properly, so that if you see the data of your plants also, if you're a power plant professional, then supercritical 1980 megawatt station would typically have 4,600 or 4,500 meter cube requirement per day for the ash handling. So that can be easily met with the other effluents which you generate through DM plant and other places. Then other macro control is the storm water. You get them collected in guard pond and use them when it is at most required. This will certainly reduce your specific water consumption. And that stormwater should not get contaminated with other effluents or other rejects. Then the most important macro controls comes to the CW water makeup, which is almost 94% of your total SWC, specific water consumption. Try to get the COC up. It is not so easy to get the COC up because everywhere the water quality is different and it depends on the makeup water quality. So it needs a thorough examination. I'll give you a glimpse what all examination you need to have, and it saves a lot because if that is consuming 94%, and if you can get it down to say 90%, your whole specific water consumption is to shift towards down. That is how I came back from 2.89 to 2. And there is a method of increasing COC with appropriate understanding of the chemistry. Another macro control is try to get the lower evaporation by not operating turbine at phase transition zone. Do not operate your turbine system, your condensing system, turbine condensing system at vacuum lower than 0.9. You don't go to 0.91 or 0.92 or 0.93, because not only you're harming your turbine blades, the LP blades, but you're also supercooling the water, where you are dissipating the sensible heat into the cooling water, which is actually not required by the Rankine cycle. Then one microcontrol which I wanted to offer is, get EDI installed in place of MB. EDI is electrodeionization, and some people, Siemens and other people, they call it CEDI, continuous electrodeionization process. That works well, and all the European countries are using that. And then review this process, the whole process on daily basis, and apply corrective actions and preventive actions whenever it is required. So how to lower the specific consumption will have, first is, you need to audit efficiency, effectiveness of your water management process, which contributes significantly to the economics. Then what should be and what it is, you need to find out. Then you should share your audit findings with what is compared with what should be. Determine the cause and effect of the findings of high specific water consumption. Then you need to train the people on how to reduce it, how to reduce the specific water consumption. Train them on all these aspects of how to do it, what to do, why to do, when to do, all these things. Then define this process using SWOT analysis and plan an improvement project. Like you can plan an improvement project of recycling the CW blowdown, or reusing your whatever the clarified discharges are there. You can reuse it through a thickener back into the system, and then finally you estimate the likely delta of improvements and do a Kaizen. This Durance trilogy you can use: design, measure, manage, and improve. And I will not go in details into that because I've got only half an hour. So I'll just go quickly into all these things. I'm still not doing much here. These are the steps which we need to take. So what are the bottlenecks in reducing the specific water consumption, which we also discussed earlier? So technically, there is no non-availability of as-built water balance diagram. I tried to search a lot when I was in Tata Power. I joined in 2006 in Tata Power. The plant was already running for 10 years, and I could not find the water balance diagram of the plant. Though there were already 4 units running, 5th unit was under erection and commissioning, and I was wondering how to do it. And I was finding 3.4 3.6 meter cube per megawatt hour is the consumption, specific water consumption. Then I did few things which made me analyze, and then I made the water balance myself by measuring it at each and every place by a portable, flow meter. Then non-availability of water meter is also a very important thing. In few plants, you can only have one or two or maximum three water meters, and they will depend on V notch or VS or something like that. But meters are actually required. Then the skills. This is also a bottleneck. The skill of the chemistry personnel and the operational personnel who may not be understanding water chemistry of complete cooling water, because this is not taught in academics. So they need to deep dive into this subject of cooling water treatment and cooling water chemistry. And thus, due to the fear of scaling or corrosion, they do not take risk of reaching high COC. So I will take you through the journey of how the high COC can be taken up based on the parameters. Then lack of awareness on performance analytics, on data received from the meters. They are not able to perform the analytics on the data. Data remains data unless until you transform into meaningful, actionable insights. Or you can call it, as few days back our health minister said, that fatigue to do the analytics. So they might be having a lot of workload and they do not want to brainstorm into the analytics of the data, whatever they receive from the meters. There are 23 meters required in a supercritical power station. Then lack of awareness of troubleshooting the problems if it arises due to high COC. And they are unable to, sometimes some of the people, they are unable to manage the ash water system. The ash water dike leaks from many places and they use lot of water. They ask for more and more blow down, and that is why the consumption of water increases, the specific water consumption increases. Then they are unable to operate the turbine into pre phase transition zone, and they are unable to avoid supercooling, and they switch off the CWS pump rather than CT fans. So first priority has to be given to the CT fans to be switched off, and then you come to CWS. This will also maintain the Reynolds number, the turbulence required for maintaining the cleanliness of the heat exchangers and condensers. Then come this system. There is a lack of capex in some of the projects where if you have come up with an improvement project of implementing UFRO for recycling the CW blowdown, then there is some problem if the PPA does not allow the capex. Then lack of funds to implement project for reduction of evaporation from reservoir, because reservoir evaporation can be reduced by floating solar PV or floating plastic big round shaped materials. Examples will be given. And then regulatory system implementation, where Mr. Khatri also pointed out, because when we run the power plant, due to the water contamination or air contamination, air pollution or water pollution, we get a closure notice, or due to ash also we get a closure notice. But we do not get a closure notice when we exceed the water consumption limits. So if government can do something on this, that will definitely have some impact on the people to get more and more people complying to the norms. And then government has recently, when 2-3 years back, recently granted the consent to operate to a new state-owned plant on old 2015 specific water norms. That is the regulatory system implementation bottleneck. So this is the typical water consumption points in power plant. I've tried to make it as crisp as possible. Summer in the left side, winters in the right side, and yearly what could be achieved is in between. Now you see always CW makeup accounts for the highest consumption in all of them, and that is where we have to act. Other places are there, we can reduce it a bit. If you reduce fire and service by zero point 0.1, it won't do a lot of benefit to you. But if you can reduce the CW makeup by reducing either blowdown or operating it in pre PTZ zone, then definitely you have an upper hand. Then if I have the blowdown water recycling, then in summer I can come down to 1.85, yearly I can come down to 1.62, and in winters definitely I can come down to 1.42 with the same configuration, where you see I'm in summer I'm able to recycle 8814 meter cube per day. In yearly basis, on the average I'll be able to recycle 7679 meter cube per day, and that makes a big difference into CW makeup. So when CW makeup comes down, the total SWC, specific water consumption, surely comes down. Now go with the flow. The first thing which we require is a water management plan, which is comprehensive as per the site requirement. Do not copy it from others. As my previous speaker said, do not copy it from others. You make your own water management plan, which is comprehensive, site-wide strategy to maximize water use efficiency. And then develop an overall plant water balance depicting the current water picture. What is the design? What is the current? And where you want to go? That you need to clearly have in your mind and in paper or in Excel sheet. I'll show you an example. I'll not go to the Excel sheet, but I will show you an example. How does it look after 2 slides? So I will not talk about those IoT specialized tools, but here to get the full picture, portable flow monitors, flow meters need to be used if you do not have meters over there. Try to get as many as possible meters implemented in the line, in the blowdown line, in the ash water return line, everywhere. So I'll show you the points where you need to get the meters. Once the plant water balance is developed and mass balance of contaminants is also tracked, like in CW, what are the contaminants, how much they are cycling up and all, then you can use the tools in conjugation with the water balance to assess how operational changes or stream redirection might allow the plant to reuse some of your internal wastewater streams, like CW water. Where else can you use? Now this is one of the balance table. Now this is half of it, and then I'll go to the half. You see, at 100% PLF, I have it at 85% PLF and 70% PLF, but I'm not going to show you here because we don't have so much of time. But the design, you see, it was 2.885, the SWC, out of which the main clarifier was taking the main chunk, and the HRSCC, high rate solid contact clarifier, is for the RODM and potable water. Now see, out of that design, say 1,34,000, in the design CW makeup was 120660. Now what we did is we tried to analyze where is the right PTZ, phase transition zone, and there we tried to restrict our fans, stop our fans. Okay, so we do not allow more than 0.90 vacuum, and we could achieve lower CW makeup. This is how then recovery of effluent is also been done, and then we raised the COC from 5 to 7.5 and then to 8, and we were maintaining an 8. So with ETP, UF and RO, we were expecting 1.792 as our specific water consumption. This is the typical water balance looks like. This is design and initial, from where the water is coming, where it is going, how much it is going, and all these places you need to have a meter. This is typical, and I will share this slides with Mr. Khatri also and Mr. Mishra, so that they can give it to you and you try to implement the same at your place. I can handhold you when you require it. This is the water balance when we improved it, when we came back from SWC 2.894 to 2.064, and this is where the excess effluent we reduced, okay, by cycling up. When we did that, further we did some analytics more, where all we can do it. It needs brainstorming, it needs discussions among thought leaders within your plant, and then you come to some analytical reviews, and finally develop some water balance analytics for, say, different PLF, what should be there. I'm not opening these Excel sheets right now. If required, I can get you that. So we could find one improvement project to reduce the specific water consumption. That was taking the CW blowdown through SSF directly to a chamber, and then through micron cartridge filter, and then through UF, and then RO, and use that 8913 meter cube back into the CW system. So this 8913 meter cube will be at a very low conductivity, and you will have a lot of chance to increase your COC as well. And this is an example of note for approval for these. We have to give all those data with cost benefit analysis. When we give the cost benefit analysis, management approves it very quickly. You see, you need to give them all the cost related data, what is currently going on and what you can achieve. And this was having a potential of reducing or saving 1.2 crore rupees per annum, only just due to the transportation of the water from dam to our place. Then we did all this, and finally we arrived at our proposed UFRO, and we could get back our specific water consumption at 1.799. So nothing is difficult in this world. It may be little difficult, but nothing is impossible in this world. You can still do it. The impossible point is you cannot reduce the specific water consumption below 1.5, because the evaporation is something which is not in our control completely. The works are going on in other places, so we may get some or other result in some time, or otherwise air cooled condensers or others. So the bottlenecks, this is the use pattern. What are the percentage use pattern of the SWC? And this is how you can reach the high COC. Now, if Mr. Khatri can help me, how much time I have, or I have to close it out?
You have time, sir. You can go, and we were waiting for Mr. Anshuman to join. He is stuck at the ministry, but if in case he doesn't, come on time, we might take a break early and resume the session post lunch. We may take a early break.
All right, then I'll cover up this important point.
Yeah.
Now, reaching high COC in cooling water system, it's not an easy job, but if you go systematically, whatever I'm telling you here are system making. No, you are creating a system and you are following the system. And we in Tata Power were calling it strategy deployment matrix. We go with the strategy deployment matrix. I learned that in Tata Power, implement that in Adani Power, implement that in Jindal Power, and I implemented that in LPGCL as well. So this is about COC, how COC can help us. It's reduction in pumping cost, natural cost. But COC, increase in COC also reduces your chemical cost, because your chemical, whatever you're adding in the cooling water system, are based on blowdown. ppm into blowdown meter cube per hour divided by 1000 will give you kg per hour. That is how the chemical consumption goes on. So if you increase the COC from 5 to 7, your chemical consumption will certainly go down. But we have to be little cautious about using high stress polymers. Means you need to use high stress polymers in those cases where your HTI, holding time index, may be going high. So this is how the first step comes. Now you have the makeup water parameters, minimum, maximum, average, and all that. And you calculate the LSI, though LSI is not applicable for cooling water system. I must repeat this. Refer NALCO handbook, page 4.17, where it is clearly written down that if the water velocity is lower than 0.6 meter per second, LSI is not applicable anymore. It is RSI which is applicable. RSI is Reisner Stability Indices, which is applicable. LSI, Langley Stability Indices, is not applicable in that manner. So where we have the makeup water parameters, we measured the indices, and these indices show that the water is actually quite corrosive. Okay, due to its low hardness, low calcium and low magnesium hardness. This is Suvarnrekha Nadi river parameters. Then we do all these calculations, evaporation. We use tower factor. Tower factor is normally given by the manufacturer, cooling tower manufacturer themselves, based on the humidity factor and the tower height. Then we calculate the blowdown. Blowdown is evaporation divided by COC minus 1. And we decide the cycles of concentration. And here the cycles of concentration should always be measured on magnesium hardness. If you have sodium measurement system, that is very good. Sodium never deposits anywhere. So sodium is the best indicator of true COC. But if you don't have sodium measurement in your system, or you don't have flame photometer in your lab, then please go with magnesium hardness, because magnesium hardness will only precipitate or will only form scale when the pH is going above 9.2. Okay, magnesium silicate also needs quite a lot of calculations. And then you go with the different COCs. You map 5 COC, 6 COC, 7 COC, 8 COC, 9 COC, 10 COC, and all those things. And use this LSI and RSI. RSI is applicable here. So you see 5 COC RSI is still corrosive. 6 COC RSI is okay. 7 and 8 both are controllable. So 7, 8, 9 both are all are controllable. So what I will do is I will raise to from 5 COC I will raise to 6 COC. I will see for 3 months. Then I will raise to 7 COC. I will see for another 3 months. Then I will raise to 8 COC and see for another 6 months. And I will measure the tools. Now for makeup and high chlorides, you need to use Larsen. Wherever your makeup water is having high chlorides in the water, you need to use Larsen's LAI, we call it Larsen tool. Okay, here I'll take you there. This is the Larsen index, where chlorides and sulfates in the water are to be taken. So if you are at a place like Haldia, or if you are at a place like what do you call Bharuch or Dahej, where you are at the confluence, there is the confluence of river and sea, where you get seawater ingress many a times, then you need to use Larsen index in place of RSI, Resonance index, and need to understand at what COC your water is highly corrosive or highly scale forming. Then at maximum values also you need to analyze it, and when you do it on average value and then on maximum value, you still have this nearly same result with this water. With this water you still have the same results, 6.2, 5.8 and all these RSI, and I can still go with raising to 6, then raising to 5.8 to raising to 5.5. Here I have to also keep an eye on silica. Magnesium into silica should not go more than 17,000 at a pH of 7.5. Magnesium in cooling water into silica in cooling water should not exceed 17,000 in any case in cooling water. If you have, then you need to have special silica dispersants to be used. Now you use all the saturation index and you find out what are the solubilities of different scales in different places. Use the indices properly and use the chemical analysis for finding the indices, and then you study the outcome of the analysis. So we were okay with the range of 7 to 10, and assuming that the maximum values a COC of 8 was ideal for us. But we do not want to go to 8 directly. We will go to 8 step by step. We'll see one step for 3 months, second step for 3 months, third step for 6 months, and then we'll raise it to 8. And note here, for CW, where water velocity is more than 0.6 meter per second, RSI should only be used. And if your water is having high chlorides or high sulfates, like what Haldia is having, or like what Dahej and Bharuch is having, then definitely you need to use LAI, Larsen index. Then the study the environmental impact, say, your consent to operate says 5 COC, but that is not limiting to you. Okay, you can still go, it says minimum 5 COC. So you try at 6, you try at 7 and see, not only the chemical cost you will be saving, not only the water cost you will be saving, you will be also saving electricity. So your company is going to become rich, right? And not only this, you're going to reduce the CO2 emission also. I can help you, I can handhold you for the calculations and all. You can contact me through Mission Energy, not directly. Let Mission Energy be between us for all these calculations and all these consultations. Then hydraulic factor plays an important role over here. How much COC we can go, and what are the hydraulic factor which we need to understand. Summation of total makeup rate and divided by summation of total blowdown rate is the hydraulic factor, and both these flow rates are comprised and controlled, and there are sometimes some unintentional components like drift loss or windage. So nowadays the drift loss of the newer tower are around 0.02 percentage of the circulation rate. So newer towers are better than the earlier towers. They have lesser drift loss and very good drift eliminator in the place. Then this unintentional uncontrolled water loss could be your SS filter backwash, side stream filter backwash, or leakage from pump glands and other things which you need to have. Like if you have 5S in your plant, if you have a 5S in your plant and TPM in your plant, your people would be looking at all these things and will be reporting to you. Then the HTI is important as polymers, phosphonates and azoles, they depend on the HTI. So earlier days we were limited to some HTI of 220 and all, but when I go to a COC of 8, the HTI becomes 305, where the half-life of the chemical comes back. The chemicals like polymers, they degrade in the water with the time. So with the numbers of hours, it degrades. So you need to go for high stress polymer for this use. All the companies, Indian as well as foreign companies, they have these high stress polymers. They're nothing but terpolymer and quadropolymer, PAA, PMA, and combination. Polymalic acid, polyacrylic acid, and combination. Then we need do further analysis. We weigh the credits and debits of at what COC, what we are gaining and what we are losing and all. And by far the biggest problem which may hinder rising the COC is unintentional intentional losses. Like in Tata Power, I had a huge intentional loss, that is the water was going down from the basin cracks. It was going down and I found it somewhere in other village, flowing with a very good flow over there, and people are using that water. So I had a problem of I could achieve maximum 3 COC in that. Then I used the blowdown of the other towers into as a makeup into this tower, so that my specific water consumption or total consumption comes down. So that may be one of the thing. And the progress should be like starting at 6 cycles and then go to 7 and then go to 8. You should not try and go immediately. But there are still some more intricacies into it. You need to do further analysis, choosing a compatible treatment program, what treatment program should be compatible with it, what and the heat transfer monitoring also you have to do properly of a condenser, the TTD, LMTD, and the U value, overall heat transfer coefficient. If you are managing the overall heat transfer coefficient as a straight line, your treatment is good actually. And above 8 COC, the stress compatible inhibitor technology should be used. That is, as I told you, terpolymer or quadropolymer, because copolymer is good for dispersing the silts and iron, but terpolymer and quadropolymer are actually you need to use. Then the diagnostic tools, you need to have metered blowdown. You need to understand how much blowdown you are giving, and you need to have a metered makeup. So when you have both metered, then makeup minus blowdown minus 0.02% of recirculation rate as drift loss is equal to evaporation. So evaporation may not be equal to this formula which I told you earlier, 0.0018 into delta T into recirculation into tower factor. It may depend on the humidity factor and the placing of the cooling towers in your vicinity, how closely they are placed. And after the diagnostic process, you need to do a measurement and control, and you need to monitor the process. And once desired COC is achieved, you maintain a high COC which is required and realize the water and energy saving. And you will be really happy when you really save water for the humankind, energy saving, CO2 saving, and also chemical saving. Your company will be happy, you will be happy, the KRAs will fly high. Then the CW monitoring tool, you need to use Corator in case corrosion coupons are lagging indicator, while Corators are real time or leading indicators for corrosion monitoring. Deposit monitoring, there are deposit monitors available with good manufacturers, and biofouling monitor which works on the DP, which will tell you, the slime buildup and all. Corrosion meter, as I told you, and test heat exchanger. If you can build a test heat exchanger, open it monthly, then you will understand what is happening within your plant, within your system. All these are interlinked towards each other: cooling tower, heat exchanger, and water chemistry. Water chemistry can influence heat exchanger. Heat exchanger will start forming, precipitation. That precipitation, cooling tower nozzles and cooling tower fills may get, if the fills are having slime, then these precipitated or the crystals will get attached to the slime, and the fills will become heavier, or fills will be fouled. So there is a big CW treatment design methodology and guidelines which our company has made, which will have the expected chemistry, input chemistry, all these things. It's a large 27 sheet. What you can see here would be the output, expected CW chemistry from the makeup water chemistry, input makeup water chemistry, data inputs, ionic loads, and all. This will calculate the input power generation. We have to put the CWT design flow sheet. We have to put the COC evaluation. COC evaluation is something like you need to do a lot of data analytics and come back to it. And then intermediate calculation for CW dynamics. What should be the pH at other different COCs. Because pH prediction is also dependent on the carbon dioxide of the atmosphere, because carbon dioxide will lower the pH. Then balance, spec source, analyze summary. Saturations, we have to do a graphical analysis through the curves. We do not have a software for this right now, but we do match it with the curves. Total burden of SiO2, LSI, and Ca, calcium phosphate, calcium carbonate, calcium sulfate burdens and all. Then we calculate the ion association. All these steps goes on to decide a cooling water treatment at what COC and what treatment should be suitable. Then stormwater, I already told you that these are the breeding elements, but stormwater, it should not get contaminated, and you can use them for your benefit of the plant. In Jindal Power, I remember we took all the stormwater in one of the pond at Tamnar, and we reuse that water whenever there is a water scarcity or there is a loss of water for the bottom de-ashings. Then we need to get prepared also for the future with, today the norm came down to 2.5, went back to 3, but tomorrow it will come down to 2 or 2.5 and again 2. We have to be prepared for this. So for the preparation, because this is a risk, right? If you do a SWOT analysis, this is the threat. If you analyze this threat, then get prepared yourself to capture the data, analyze the data, apply analytics over, where you can go on and high, and then reduce the specific water consumption. With reduction of specific water consumption, you are not only reducing the water footprint for your plant, but also reducing the energy footprints, the CO2 footprints, other things for your plant. Then side stream filtration. Typical conventional side stream filtration consumes about 10% of the water, whatever it flows from it. Say suppose you have a plant of 1 into 660 megawatt, you have 88,000 meter cube of flow. So 4,400 meter cube you will be flowing through this side stream filtration. Now, if this side stream filtration is, taking 10% out, means 4,000, you will be using 5% of it. So 4040 you'll be sending through it, and you'll be losing about 440 or maybe 500 meter cube per day. So that is 10% of the circulating water which goes through this. Now we have special kind of not just chem, but in India Gopani has bought it, and in the world many has bought it. This self-cleaning kind of filters. You see the video and try to understand. So with this is self-cleaning, so it does not require regular maintenance, no manpower required for monitoring it, and when the DP comes, you will tell, and then you will go for a backwash cycle and all. So it is continuous filtering and continuous backwashing, and it assures optimal filtration efficiency because it has pore sizes, precision pore sizes made in this stainless steel. This is self-cleaning. It does not, it reduces the energy cost. No monitoring required, only 3% water waste. And the most important point is the capital expenditure is similar to what is your conventional sand filter or conventional multigrade filter has. So at the same capex, if you get so many benefits and you can reduce your water footprint, what best you want? You got a full toss. You cannot miss it, right? This is what Virat Kohli said today morning. I saw one of the. So these are for reducing the evaporation loss from the reservoir. These kind of things. The first floating discs are used, and then shade balls are used. Floating disc, they can reduce up to 80% of the evaporation from the water surface. And shade balls, they can only do 43 to 45% because these balls are rolling in the water. When it is rolling, it is having a thin film over it. And when it is a thin film, the thin film evaporates faster than the bulk water. Then the shade cloth, this I saw in Indonesia, where in April, Indonesia, the world largest paper mill. I'm also a consultant of that company. So in that company, I saw this kind of cover, full cover. This is called shade cloth, and which reduces 90% of the complete thing. And the Spain and Australia, they did a lot of study on this, and also in India we are trying to do some study in some places. Then these are the solar PVs, and this can reduce the evaporation of your reservoir. Not only the evaporation, it will also give you a lot of energy, power.
Mr. Banerjee, you have few more slides to go.
So I'm now open for any discussion or doubt clearance. Yeah, you may please ask me.
Yeah, I probably have few questions from
Are you
the
there? I'm not lost, right?
No, you're not lost. We're able to hear you. So we have few questions from the audience, especially for Mr. Banerjee. One, Mr. Nawab Ansari is asking, Banerjee sir, is there any direct method to control and measure the evaporation losses?
No.
We are taking the design value of evaporation losses in the calculation of water consumption. How is the measure the evaporation losses?
Okay, I'll go back to share the screen, and then I'll go back to one of the slides back, and Mr. Ansari is requested to note down this equation, which is a beneficial equation and been used each and every place. Yeah. Evaporation is equal to 0.0018 into delta T in degree centigrade into recirculation rate in meter cube per hour or in meter cube per day. If you want evaporation in meter cube per day, you can use recirculation rate in meter cube per day, and the tower factor. Normally, if you are in the region of coastal region like the coastal Gujarat, coastal Andhra, or otherwise towards coastal Tamil Nadu or Kerala, your tower factor is going to be low. It may be 0.82 or 0.85. And when you are in a dry area like the mid of India, like Nagpur or like Jhansi and other places, the tower factor is going to be like 0.94. Is that okay, Mr. Ansari? Have I answered you?
He has actually put this in the chat, so I'm not sure. He should have heard you.
Okay.
I request the audience to raise their hand so that we can take questions. I will wait for a minute or two to have the audience to raise their hands. If probably I don't see anybody raising their hands, we might take this session for early break, and we will resume the session post lunch. I'm waiting. Very importantly, I also request the audience to change your mode into light mode in case there is a connectivity issue. I have Mr. Manoj Agarwal. Yes, Mr.
Yeah, am I audible?
Yes, you are audible.
Yes, my simple question is that we have been talking about the COC reduction and water conservation. That
COC increase. Increase in COC.
Yes. Sorry, increase in COC. That is water conservation means increase in COC traffic. So whether we do have any technologies available, that because water quality itself keeps a very important role in deciding the COCs. Hardness level and other we are using 100% HTP water as we discussed.
Yes,
so
I know.
Organic loads and other parameters in HTP water which are bothering us. So because in HTP water we have particular problems with respect to condensers as well as our boiler feed pumps and small like compressors with small cooling lines. So these all are getting frequently choked. So do we have technology using which we can at least provide maybe incoming side of the BFP and cooling water pump or BFP this compressor, so that this water can be little bit softer? Any portable solution we have which we can install at the inlet of the equipment, critical equipments.
Now, this requires a little more analysis, as I have visited your plant twice or thrice, maybe with Washer Technochem. Washer
Okay.
Technochem was your vendor
Yeah.
once upon a time.
Yes.
He took me there as a consultant. No, he was challenged with this. All these sewage from Udaipur is coming to you, and you are then treating it and reusing it in your power plants and other systems. So I know a bit of it, and their RO plant also had a lot of problem earlier. So I know about this. Now, when you talk about your boiler feed pumps, and if you're talking about steam water cycle, because that choking is certainly should not happen because you use DM water, right? And
No,
DM
no.
water.
I am talking about the cooling water being used for cooling of this equipment. Like
Okay.
mechanical cooling is there. In compressor also.
Yeah. I understood. It is like the other circuit, the out of circuit. Yeah, the cooling circuit of the motors and pumps, pump bearings and all.
Yes.
So, sir, actually, you need to use uh, one thing called DBNPA.
Okay.
Okay, this is a very good slime cutter, and
Okay.
and if you use only say 3.5 to 5 ppm between them, it will give you a very good result. Actually, I again wanted to go to your plant with clean flow, because now I'm associated with clean flow. So I wanted to go to your plant, but I could not visit due to this COVID-19,
Okay.
because you had a large you made a large inquiry, and where only few of the vendors were asked to come and
Okay.
quote.
Okay.
So I wanted to come there, but anyway, you can always talk to Mr. Khatri. You know Mr. Khatri, right? Mr. Ashwin Kumar Khatri.
No, I think I don't.
No, he's the Director General of Mission Energy Foundation, who is managing this show now.
Yes.
Okay, yeah, you can get my phone number and other things from them,
Okay.
because or
Mr. Banerjee, you are free to share your email IDs, mobile numbers, everything via chats in the portal. You can also share it on the WhatsApp group, which we have already created for the participants.
okay, I'll do that.
What did you tell? BP, ED.
No, DBNPA. DBNPA.
What is this? This is some chemical.
Dibromo. Yes.
Okay.
This is a kind of slime cutter.
Okay. So that we can use in water, but the huge quantity of water we are using 2 into 80 megawatt, 26,100 is the circulation water.
If you give me a consultancy order, sir, I'll help you out, sir. Surely.
That's a good thing, Mr.
I think that we can think of, but being with the opportunity on a platform where we are having brainstorming and good
No,
consultation.
because sir, anything related in water does not have an immediate answer. Okay, it needs analytics. As you saw, even for the COC and planning for a cooling water treatment, we have to do 7 days analytics, and then we come down to some calculations. So we need analysis of the water. We need the water consumption data or water balance data, and then we apply our minds. How economically we can solve your problem. So that is.
So what we will do, Deepak Kumar is there from operation side from my plant. I don't know whether he is active right now or not. But I will ask Deepak to, or you can share your contact number in the WhatsApp group. We will get in connect with you.
I'll do that, sir.
We will get in, definitely call you as a consultant. It's not an issue. With some agenda points. And meantime, during this presentation or during the session, if you can if anybody out of the present members can suggest any solution for small and very thin lines, how to avoid choking of that lines because of STP water. If anybody has any solution, so I will understand myself. Attending this whole 2 day session will be successful for me.
Yeah, Mr. Manoj Agarwal, you can be on the tables during the networking breaks. These tables are personal interactions between each other, which are not been recorded or not been known to us. Also, what I've been talking. So on the tables, you can discuss whatever you would like. So we will break for the session, and I have a question again from Mr. Ajay Kumar Sharma. Could you please repeat? In which case the LSI or RSI is applicable?
Okay. See, if the water velocity is less than 0.6 meter per second, LSI is applicable. But if the water velocity is more than 0.6 meter per second, Reisner stability index or Larson index applies. Able to get me?
He should have heard you, because these are the questions which are there in the chat box which the participants have sent.
Okay, Mr. Manoj Agrawal, if you can connect with him once again, if you can tell him that there are engineering solutions also available. It's not only chemical solution which he needs to use. There are engineering solutions available to avoid choking of his narrow pipelines. We can discuss on that.
He stage, but all the participants can hear our conversations, and they can come on the stage by raising the hands. I have not been seeing anybody raising the hands right now. So probably we'll take a break, and you could enjoy networking during the lunch, while there's probably another chat which is there. Okay, there's no question. So probably I don't see questions, and we can now take a break for lunch. Participants are welcome to interact with each other, network with each other in the break times, and enjoy themselves during these break times. We will resume the sessions exactly around 2:30. We have one presentation which has not been made by Mr. Anshuman, but he'll join by 2:30 to do his presentation also. So enjoy yourself. Thank you. I'm taking a break now. Thank you, sir. Thank you for being there. Welcome back. We would be starting the sessions where we left. We couldn't have Mr. Anshumanji's presentation because he was stuck at one of the ministries. Now Mr. Anshuman is back with us. Mr. Anshuman, the Associate Director, Water Resources at TERI, is along with us. I welcome Mr. Anshuman for the session.
Thank you, Ashwini. My pleasure to be part of this program.
Yeah, so we are resuming the earlier session where we took a break. I hope after lunch it is not going to be heavy, because after you there's another session with 4 speakers. I request Ms. Anshuman to proceed further.
So thank you, Mr. Ashwini. I believe I have around 30 minutes time.
Yes.
Sure. Let me at the outset first thank Mission Energy Foundation and the program for having me on board. What I'm asked to is basically talk about some of my experiences that I've had on some of the industrial, let's say, audit and water use efficiency work. So I'm trying to basically, share that experience with you. Allow me a moment to just share my screen. So as I said, I thought of sharing my experiences with the industries. Larger focus will be, of course, on power plants. Let me just quickly go through, as to what we at TERI do, but I will not spend too much time on that. There are a number of issues that TERI works on, especially in the areas of water, and they are related to water use efficiency. I'll talk about it in more detail. We have had several industries on this in terms of improving water use efficiency, as well as many cities. A lot of these audits that we have taken in the urban sector actually has helped the cities and build their capacities on efficiency improvement. We are held in rural sector, drinking water supply and sanitation. health and hygiene related aspects. Tried our hands on having a decentralized drinking water system run by the community, integrated water management into which a lot of interventions on conservation, water and climate change, quality and pollution studies, recycling reuse. I'll talk about it more. A lot of assessments, independent assessments, and of course training and programs. We have a lot of infrastructure that we use in the process of investigations and supporting on solutions, and we share our experiences with various forums, especially the India Water Forum that we hold regularly. So the problem with the water sector actually is multifold. We are having various kinds of collective issues that we face across, ranging from water availability, which is declining per capita over the years, basins which are water stressed. We have increasing and competing demand amongst the sectors. The resources that we have available to us are really overexploited, and a lot of inefficiencies in our water use. As I said, we are in a region which is having 1/4 of the world's population, but just around 4.5% of the water resources, and we are water stressed already. Talking about the industries, how much is the water use? I mean, we really don't know so much because a lot of this information is not in public domain. But whatever we know that there's an increasing demand that is going to be with us very soon. We need somewhere around 228 BCM of water. At 1999 level, that is just around 67. Where are we going to get this water from? And this, when our industrial water productivity is really quite low. If you look into the value, we are somewhere around $7.5 per cubic meter. It might have improved a bit, but then if you compare it, across the world, they are somewhere around 2030. So we are still far, below. In general, the water productivity in South Asia is less than $4 as compared to $24 for the top 5 world food producers. Our own country's, demand on industry is projected for various fold increase. As you can see, we need somewhere around 115 BCM by 2050 is what the report on what working group of water resources had done, evaluation sometime back. What we know also is that we still consume around 2 to 4 times more water per unit of production as compared to the similar plants in other countries. In fact, the World Water Development Assessment Report in 2015 talked about actually having an increase by 400% by 2050 of global water demand in the manufacturing sector. Now, that's the kind of situation where we are placed in as far as industry is concerned. And this, of course, as I said, when we have overexploited groundwater resources, several of our regions that you see over here in red or blue, they're all overexploited or critical or semi-critical conditions. A lot of our water bodies are polluted. I'm not going to go into details. Most of you would know this. The challenge with this is that this incurs a cost on the input water that we take in for the industrial production. And therefore, it remains a challenge for most of us. And in fact, a lot of untreated wastewater or partially treated wastewater that goes into the river causes the pollution at various levels of water quality parameters. And therefore, pollution is something that we continue to see. Now, the wastewater component is something also in the context of the industries is very important. If you look into this is the world scenario in terms of where we are. If you look into possibly where we are in the upper middle income countries, we are just treating of around 38% of water. But that's the general scenario across the world. If we talk about our own self, especially the sewage that we are generating is we are treating just about 37% of that. So the point is, if we are able to reuse this resource, treat this resource and reuse, there's an opportunity to have a better efficiency and also meet our demand supply gap. In the context of efficiency and industries in particular, the National Water Mission under the Minister Jal Shakti is actually focusing on a lot of these aspects of water efficiency improvement. Recycling and reuse of wastewater, mandatory water audits are something that which is already very much specified, and a lot of interventions are on looking into what are the benchmarks that could be established for industries to be taken forward. And we are working on that with the ministry and a lot of industries as well. Of course, the SDG goals India is committed to will be requiring including industries to be efficient on all these perspectives of pollution reduction, water quality, and water quantum management, especially in the context of water use efficiency. The question is, what is needed to be done? I think the importance of improving the efficiency lies in the fact that we need to be reducing our waste and moving from reducing our waste towards resource recovery, which is actually a current opportunity. I mean, a lot of these technologies that we have in today's context actually gives us that opportunity to have move away from just looking at wastewater treatment to actually a perspective where we can look into resource reuse and recovery as well. That's a resource for us. Of course, improve the productivity and efficiency, and as well as look into the possibility of conservation interventions, including zero discharge and reuse perspective in every sector. And I'll talk about it in more detail. Now, what we have looked into by our audits with various industries, and of course, I will talk about thermal power plants in more detail in a while, that there is a significant amount of opportunity in actually improving the water use efficiency and saving water significantly. Maybe I cannot generalize, but most of the industries that we have audited, we found there are various areas of operations where the opportunities lie. For example, of thermal power plants, we have looked into number of power plants that we audited. We found a significant opportunity of saving water, ranging anywhere from 18% to 30%, 35% even in some cases. And actually, the specific water consumption can be reduced significantly. I'll talk about it in more detail. Heavy engineering, somewhere around 45-46% of water saving. Healthcare, in fact, we looked into the footprint as well of the industry in value chain. Significant potential of saving of water by various interventions within the industries and outside the boundary of the industries in the value chain as well. Not many other industries. These are just few of the examples which we have audited. I'll talk about them not in more detail, but with few examples a bit later. Pulp and paper, significant opportunities in water saving by recycling and then using, for example, ultrafiltration in closed loop, recirculation of wastewater. I mean, the range is quite very high, depending upon which level of efficiency they are in. It ranges anywhere between 5% to 75%, and so is the case with the textile sector as well. A lot of opportunity on reusing the wastewater, and that can reduce the freshwater demand significantly, as you can see, around 85 to 90%. There are also various examples wherein cross-sectoral, for example, between industry and the cities and the municipal corporations, there are arrangements of having treated wastewater from the domestic sewage and domestic sector to use within the industry. Chennai Metro Water, CPCL, MFL, and RCF in Mumbai. They're all very good examples of having this arrangement where they are using the treated sewage for their industrial input, and they're all benefited by lower cost and ensured of the water for their systems. So the point I was trying to make is, in the current context, since we still continue to be a bit inefficient in terms of the water use, especially in the industry, actually is the case with all the sectors, I think there are significant opportunity. Let me give you some examples from our own audits, and I will focus on thermal power plants. Just to let you know, I mean, just an example of Israel, we all probably have been referring this for some time. I mean, this country had its, population increase 4 times since 1964, but the water demand didn't actually increase in the sense that they were actually using around 80% of their wastewater to meet their demand-supply gap, and the water loss is very, very low and one of the best in the world. So these are the kind of approaches that we need to be inspired with, and I think there's a significant opportunity that we can look into in the industrial sector as well. Right. The case of thermal power plant, as you would know, thermal power plants are the largest water-consuming entities as far as industry is concerned. Somewhere around 80-85% is what they consume in general. We've audited not many of them, and I'm very happy that most of them have been very proactive in terms of taking the water audit, and the credit goes to them to have initiated that process. But I'm sure they have benefited, and I think this is a very good example that could be imitated across the sector and within the sector as well. So this thermal power plant that we audited, was actually one of the country's largest power plants. Wherein we looked into their entire operations, right from water intake to raw water treatment, clarification of water, DM water, drinking water system, but more importantly, the cooling system and the ash handling system, which consumes a lot of amount of water, and looked into the overall water consumption, both in terms of quantity and quality, to look into the opportunities and where we are at the first place, and to what we can do to improve our systems. We looked into the other aspects like cycle of concentration and what is the scope of water conservation. I just want to briefly mention that audits are something which are very, very important tools. It's like a health checkup that we must do for our systems to see where we stand, and more importantly, fix up or identify the prioritized intervention where we need to invest into. I mean, we all know there are efficiency improvement needed to be done, but where should I put my money in at the first place? Whether it is leakage losses or whether it is a system improvement in some operation or a combination of these, and likewise. So I think audits are a very good tool to give you that information and save that kind of investment, which otherwise might be really otherwise not required at times. And then of course you save water and you improve the efficiency simultaneously. Now talking about the power plants, and just for those of you who might not know, basically power generation happens through steam moving the turbine, and this steam basically generated in boilers, and after moving the turbine, this steam is condensed, and the water is taken back in a closed loop to the boilers. This boiler gets the water from DM plant, which is very clarified water, and the entire process basically relies on the fact that the steam basically is condensed. Now condensation happens with a cooling system wherein the cold water comes in, and the condensation basically happens, and this hot water after condensation is taken back to the cooling towers for further cooling, and mostly this is in closed loop circulation, although earlier a lot of these open channel circulations were there. Now this closed circulation water basically happens to have evaporative drift losses from the cooling system, which is actually made up from freshwater source, which after raw water treatment is taken to various uses within the plant. For example, filter house, which treats the water and gives to various uses, including DM water, drinking water supply, and likewise, and also to the ash handling system, and basically water transport to the ash transport to the ash dike, and likewise in other aspects of coal handling, ash fighting, firefighting, etc., and various other auxiliary uses. Now, this is the system usually in a thermal power plant. Now, we audited these systems, and the plant that we audited had such, 3 stages. In fact, later on, they had increased more, 5 stages. I'll come to that. So each of these systems, it's a very complex process of establishing the network, identifying the pipelines, and the strategic points of monitoring to give a complete picture of the water usage in different setup, different processes. Well, we did that identification in all these 3 stages then, and identified the locations probably which will give us the best picture of water quality and water quantity. Now, of course, we monitored these locations for both quantity and quality, established the water balance of the system, and this is what we found. Now, typically, that's what it will look like for thermal power plants in some variations, but in this particular case, what we found was roughly around 50% of water was being used in cooling systems, around 30% in ash handling, then, of course, various other uses, including drinking water and auxiliary uses, DM water, etc. Please note firefighting over here, suggesting possibly there was a case of fire, which wasn't actually the case. I'll come to that. But overall, if we look into the specific water consumption, the SWC was around 4.8 to 5 meter cube per megawatt in the range of industries that we have audited, just to give you a general range. But what we identified was that this particular consumption could be very well reduced to 3 meter cube per megawatt or even below that in many cases. I'll come to that. But how? The first most important intervention that was identified was a no-brainer. It was basically the wastewater which was discharged unused, and you can make out from the quantity around 18% of the intake water, 64,000 meter cube per day, significant volume of water. And for those of you who would understand the water quality parameters, it had a TDS of around 150, 200. I mean, for this kind of TDS, you'll have to put a treatment system and incur some cost to basically bring the water quality to that level. So that kind of water was actually getting out of the system. But obviously, it's not something that was done intentionally. The systems, monitoring system wasn't in place where this could be actually gauged. And once they gauged it, they immediately plunged into basically tapping this as an opportunity, as a resource. So this was one of the biggest opportunity that was lying in the power plant. And of course, I would have to say that this is just an example, which is a representation, but most of our systems in our water supply management, be it irrigation, be it domestic sector, or even industrial sector, the leakage and losses are a very significant and prominent, issue that continues to be there. And I therefore keep saying water demand management is something that has to be really focused on at the first place in top priority, and then followed by other supply side interventions. Now, you might be able to see quite significant overflows, leakage losses, from the pipelines, and as well, overflows from the system were quite prevalent. And obviously, because there wasn't a system in place which could look into such, losses, the opportunities were being missed. And I have to credit the power plants who actually got them investigated to see this opportunity. I keep sharing a few more pictures. I'll come to that later. But looking into what was the water used before audit, as you can see, their total intake was around 380,000 meter cube per day of water, which was used in all of these, processes, as I said, and of course a significant volume of water basically was being discharged as well. What we identified was that through audit that this could be reduced, roughly around 50%, to around 147,000 meter cube per day of water through plugging leakages, rationalizing township water, but the biggest basically coming from the cooling systems in which the cycle of concentration could be increased, and of course the recycling of wastewater, and also a considerable portion of water which was otherwise being overflown or lost from the ash handling system could be also put back into the recycling system. And there are of course other interventions as well. So what we found was that, for example, water for boiler auxiliary could be reused, ash handling, a significant water loss, 50 to 80% could be brought down. And the COC, the cycle of concentration, could be increased. I've been interacting with people, handling power plants, across the world, and some of them has, very frequently say that, it could be taken very easily up to 10 or even higher. But in our case, let's say, we have some of the best cases who have reached 6, 7, 8, even higher in some cases. And I think that's an opportunity which can be really picked up. Increasing the COC, cycle of concentration, could be easily done by effective maintenance of the cooling systems. I'll come to that. The other area was basically all the power plants have usually a very high, very large township, and the per capita water consumption in townships usually tend to be very high. And what we found was that, for example, they had a consumption of somewhere around 1,300 LPCD, liters per capita per day. And what we found was if that could be brought down to even 150 LPCD, even though the urban setup has 135 LPCD as norm, even then a significant volume of water could be saved. But like I said, the largest potential was from the recycling of the wastewater. We could achieve a zero discharge status as well, and as well as the ash handling and the cooling system. So a combination of these, basically what we found was that it could reduce around by 60% of the water being consumed into the system by interventions in all of these key areas. And what we did was we actually designed a recycling system for the industry. Not going into details of this, but there are various technological possibilities in these days which could bring in recycle and reuse and zero discharge as well. So there was an immediate potential of saving water by around 30%, roughly around 30%, 23% of the total intake water, for example, over here, and in total around 60-65%. And there was significant financial saving attached to it. For example, what we calculated for this particular case was around 7 to 9 crore rupees annually. And there was a cost benefit of the recycling system that we analyzed with a payback period of less than 3 years, which is quite attractive. Maybe I'm not generalizing this for each and every case, but in most of the cases, we do have an understanding that it can save significantly the resources and give you a financial benefit with an attractive payback period as well for the intervention. In fact, I'm very happy that, I wanted to share this with you that they called us after first audit, after a few years, to see where they reached after the interventions which was suggested were implemented. While they were still in process of doing that, what we found was that they saved in all of these areas that we suggested a significant volume of water, around 120,000 meter cube per day of water. They achieved the saving of that water. And while they had further, opportunities to improve that, which came out with the second audit. And that's why I keep saying it's a health checkup. Systems keep having, their own bottlenecks and breakdowns. So if you do an audit regularly, you will get to know what is my current status and where I need to, focus currently and invest into what kind of intervention. And this time we found that they had further potential of around 91,000 meter cube per day. So in all, they actually, what we had in a way predicted for them, they brought it down from 4.8 to 3.2 meter cube per megawatt, quite a significant achievement. And I'm very happy, I keep sharing this for the power plant. Well, the second audit that we did was basically we found out that they could further go in improvement from 3.2 to around 2.3, and this is the process which keeps going on. But I think the point is, if you are able to initiate this process, you will be able to reach to a level where the efficiencies are at the benchmark comparison level, and you will be really very efficient as far as water use is concerned. In fact, these are just the numbers. For example, a significant percent of water saving in all the areas. Associated with that is a significant financial saving as well. So it's quite attractive, if you intervene into this kind of approach. We have a publication on this. If you want to have that, you can very well refer to that. There's a policy brief. It can be, downloaded from here. There's another publication which refers to the similar approach in case of power plants. I'm conscious of the time. You just left with 5 minutes, so I'll not go into details of the other case studies because I'm told possibly 5 minutes should be there for question answer. I did have other case study, but let me give you a wider perspective as far as power plants is concerned. As I said earlier, we have audited many number of power plants, and as you can see in different ranges, the opportunities for reducing the specific water consumption remains there, and it's very much doable. Mostly classified into, let's say, into short-term and long-term intervention. What we found was that short-term interventions could be taken up is, for example, the recirculation of water as far as ash handling system is concerned, up to 70%, increasing the cycle of concentration, starting with, let's say, up to 6 and further going on further higher, recycling of wastewater, especially looking into zero discharge perspective, and in different capacities of the power plant. What we found was there's all these significant opportunities to reduce the specific water consumption. In the long-term basis, we can move from wet ash handling to dry ash handling systems, and also from conventional wet cooling system to dry cooling systems, of course, wherever applicable and as the feasibility would be. I'm aware it's not feasible everywhere, but wherever the feasibilities lie, I think in the long term that could be looked into. And again, a combination of these short-term and long-term interventions are the opportunities for the power plants. As I said earlier, recycling of ash water, moving from wet ash handling to the dry ash handling, moving away from once-through systems to firstly a closed cycle system, and then of course focusing on a higher number of cycle of concentrations, basically the recirculation, which could be attained by chemical treatment, anti-sludging, anti-acidification, and of course maintenance of the cooling systems, cooling towers, the wastewater recycle reuse. The fire hydrant, which must not be used for any other purpose. Usually what happens is we tend to use the fire hydrant water, which actually is a pressurized water, should be only used for, let's say in the event of emergency of fire. At times we use that. So although it's not a wastage as such, but it's a misappropriation of water for a different usage. What is very important is that we have a regular water audit undertaken, and have this internalized in the corporate policy. And of course, automation in current context is very, very useful. Use of ICT solutions, sensor-based monitoring systems, and having a decision support system which is real time is very helpful. And some of the industries have already started doing that. So I'll skip this part because I didn't, I don't have time. But I think I'll rather focus on the way forward. As I said, we need to have, focus on enhancing our water use efficiency and reducing the water footprint. Maybe we can move from, starting from our industry, we can move towards the entire value chain. The idea is to have efficiency improvement in all of these areas that I talked about. This helps in the national goals as well as, for example, the National Water Mission goals, contribution towards the reduction of the wastewater, as I said, through the interventions. This also helps industries with the benchmark, which I talked about. We are already, working with several of the industries to look into what are the possibilities of attaining or setting up a benchmark at the first place. And that shall be, very helpful in terms of having a best practice or a benchmark to be propagated in every sector, and shall be helpful in dissemination of knowledge further. Audits, as I said, must be taken up. And of course, what we keep also suggesting the government is basically having a Bureau of Water Use Efficiency, which looks into the perspective of efficiency improvement, capacity building, etc. Data sharing is very important. All those who have achieved this efficiency should be sharing it with the others, so that this could be widespread, achieved as far as industrial water use efficiency is concerned. And we must incentivize those who actually have efficient water use taken up. India is also committed to, basically having and improving the industrial water footprint in the INDC. So it's another part of our commitment. We must also look into the regional water management, where not only our own presence within the boundaries, but also in the watershed approach, we are able to look into the risks and also manage the water holistically and not become a risk for anybody else, and also the water being risk for our own operations. And I think in that sense, having the local community engagement-based, PPP interventions or CSR interventions is another opportunity. A lot of programs already are there from the government side, which could be bridge between the interventions on water sector, and as I said, automation as well helps a lot. So I'll stop here. Maybe if there are any questions, or Mr. Ashwini, if you would want me to respond to them, or I hand it over back to you.
I would welcome the questions from Mr. Anshuman from the audience. Can I stop your presentation so that I can?
Yes, please.
Mr. Hemant Jetia, I'm just handing the mic to him. Yes,
yeah,
Mr.
thanks, Ashwin. Yeah, I hope you can hear me.
Yeah, we can. There is no point asking this question. The technology takes it all mode.
Yeah, sometimes you never know whether you are speaking, but people are listening. Okay, yeah. So just going by all the presentations this morning and the way you were explaining in the morning recommendations for this water issue. So what I see is this water balance, the complete audit of a power plant, that is a must. There has been a lot of talk regarding this water audit to be made mandatory, but I understand as of now, it's still not mandatory for all the power plants. So what could be one of the recommendation is to have all the power plants get this water audit done every year, and then maybe publish the reports in public domain, so that there could be kind of pressure, and there could be others who come to know about their water consumptions could come up with the solutions to these power plants. So that should be something we have been discussing for past few years, but then this has not, as of now, not yet implemented. That's what I understand.
Okay.
Yeah, that's true. I think I very much appreciate what you're saying. In fact, it's been some time. Not only the mandatory water audits, but also this Bureau of Water Efficiency, something that is being looked forward to be established. Right. From my interaction with the ministry, I think what I understand is that they are very much in the process of doing this. I think it's only a matter of time it should come forward. But I think they realize the importance of this, and hopefully it should be coming up sooner.
Okay, thank you.
So I don't see anybody else having raised their hands for the questions. I thanks all for being hearing watchfully Mr. Anshuman for his brief presentation. I thank Mr. Anshuman for being with us, and I would end this session and take the next session further. Thank you, Anshumanji. Thank you so much.
Thank you, Ashwini. Thank you, everyone, for your attention.